We recently found that devices in our electric circuits behave differently when they're connected in series compared to when they're connected in parallel. In these situations, the voltage, the current, and the resistance all combined differently in these two scenarios. So the goal of this lesson is to recap what we found. And we're going to start by just doing a quick diagram to remind ourselves what series and parallel mean. So let's illustrate this with some resistors. If I had 3 resistors in series, they would occur one after the other without anywhere else for the current to go. Like so. If I had 3 resistors in parallel, it's a bit of a different situation. The current would come along and then it would split. And it would have 3 different options. And then at the end of those options, the current would recombine and head back out into the circuit. So that's what 3 devices or 3 resistors in series look like compared to 3 devices or 3 resistors in parallel. Now, in each of these situations, I could ask myself about a number of quantities in each of the resistors. For each resistor, I could ask about the voltage, the current, and the resistance. And I'd have a voltage and a current and a resistance at each resistor. And to help me remember which is which, I could maybe call them voltage 1, current 1, and resistance 1, all from the first resistor, voltage 2, current 2, and resistance 2 for the second resistor, and then 3s for the third resistor. And in the parallel scenario, we'd have the same thing. Every resistor would have a voltage, a current, and a resistance. Now, in addition to knowing about how this resistor behaves, or how this resistor behaves, I might want to know about how all of these resistors in series behave together, if I treat them as one big, long device. And similarly on the parallel side, I could ask about how this resistor behaves or how this one behaves, but I might also be interested in how the entire thing behaves as if it were one device. And that's where these rules that we have below come in. These rules tell us in each of these 2 scenarios, series and parallel, how the total resistance of this entire part of the circuit, or the total voltage or total current, is related to the individual voltages, currents, and resistances on each of the resistors. So on my series circuit, I'm going to have a total voltage from the very top to the very bottom. A total current, which is what I'll observe at the very top or at the very bottom. And a total resistance, how much resistance all those resistors have when they're combined. And similarly on the parallel side, if I look not at each individual resistor, but from the very top to the very bottom, there will be a total voltage from the top to the bottom, a total current, which is the current I'll measure at the top or at the bottom, and then a total resistance, the combined effect of all of these resistors together. And the formulas that tell us how these behave, how these total resistances and voltages and currents can be calculated are as follows. In series, the voltages add up. So the total voltage is the voltage at the first resistor plus the voltage at the second resistor plus the voltage at the third resistor, and onwards if you were to have more resistors. If you like the ski hill analogy, that makes a bit of sense. It basically says that if you take the height drop on this ski run and the height drop on this ski run and the height drop on this ski run, and you add them all together, you'll get the total height drop for the whole thing, from the top up here to the bottom down there. When we talk about the currents, the skiing analogy can be helpful too. Because there's only one path for the skiers to take when going down these three runs. The number of skiers going down this run has to be the same as the number of skiers going down this run, which has to be the same as the number of skiers that'll eventually go down this run. And if I wanted to look at the total current, the total number of skiers, either right at the very beginning here or right at the end down here, that would be the same as well. The number of skiers that go through each of these zones has to be exactly the same because there's nowhere else for them to go. So the way we say this mathematically is the total current is equal to the current in the first resistor, which is equal to the current in the second resistor, which is equal to the current in the third resistor, and so on and so forth. Now, when it comes to figuring out what happens with the resistance, how the resistance combines, I find the skiing analogy not super useful. And an analogy that can kind of help is to think about a metal chain. We've talked before about how metal chains can be a bit of a useful analogy for electric circuits. So if you think of the current as sort of a metal chain that's running down this line here, and each resistor is like someone's hand grabbing onto the chain and providing some resistance, so the chain has to slide through the hand, then you can sort of see how the resistances from these three hands will all combine together. If the first hand is providing a resistance of 5, and then the second hand is providing a resistance of 5, and the third hand is providing a resistance of 5, the total resistance that chain will feel is the sum of those, 5 plus 5 plus 5, or 15. So mathematically, we say the total resistance is the resistance from the first resistor plus the resistance from the second resistor plus the resistance from the third resistor. Now let's have a look at that parallel circuit. Again, thinking about the skiing analogy, if I'm coming along here and I have a choice of 3 ski runs to take, run number 1, run number 2, or run number 3, and they all start at the same place, and they all spit me out down here, then that means they're all going to have to drop me the same height. They're all going to have the same potential difference. They're all going to have the same voltage. So in our parallel circuit, the voltages are all the same. Total voltage is equal to voltage 1, which is equal to voltage 2, equal to voltage 3, etc. Now the currents behave a bit differently. Let's say I had 10 skiers come down this way. Some of them are going to take different routes. Maybe I have 5 skiers go on this run, 3 skiers go on this run, and 2 skiers go on this run. Depending on what exactly those resistances are, that will dictate how many do each run. But the key thing here is the number of skiers on each run, if I add them all together, has to give me 10, because that's what I started with. And that's also what I'm going to end with. So the total current at the beginning and the end is equal to the sum of the currents on the individual resistors. Mathematically, we can write this as follows. The total current is equal to the sum of the individual currents. So all the currents added together. And so we're starting to see a little bit of some symmetry here. In series, the voltages all add and the currents are all the same. Whereas in parallel, the currents all add and the voltages are all the same. Now the last thing we need to talk about is how resistances add or combine in parallel. And this can be a tricky one to wrap your head around. I find the skiing analogy doesn't work great. I find the metal chain analogy doesn't work great. The analogy I actually like to use here is what I call the grocery store analogy. And the grocery store analogy goes like this. When you're walking through the aisles of a grocery store, doing your grocery shop, the one part of the experience that provides resistance, that slows you down, is the checkout, is the cash register. So when you're finishing your run through the last aisle of the store and you're approaching the cash registers, let's say you're in a scenario where there's only one cash register open. This one over here on the left. That'll provide some resistance. It'll slow things down. And if things get really slow, the store manager might open up a second till. Suddenly you have another option for where to go for your checkout. Now, even though cash registers add resistance, and we've just added another cash register, it doesn't increase the total resistance. This actually means there's less resistance. It means the flow in the grocery store will be a bit faster. Because that resistance that's added isn't mandatory, it's another option. And people will only go there if they think it's going to be faster. And then if things got really slow, we could add even a third cash register, and now people have 3 options for where to go. Even though this adds a resistor, it doesn't add overall resistance because it's added as an option. It's added in parallel. So it's a bit of some strange behavior that we see for resistors in parallel. The more resistors we add, the less resistance we have because they're not mandatory, because each one provides a new option for the current. Now, the way this works out mathematically is a little interesting, a little bit peculiar. The formula looks like this. It's got a bunch of fractions. So 1 divided by the total resistance equals 1 divided by the first resistance plus 1 over the second resistance plus 1 over the third resistance. So, quick recap. In series, voltages add together, currents are all the same. In parallel, currents add together, and voltages are all the same. And I think that the ski hill analogy works well to help you understand that. When you have resistors in series, every new resistor adds to the overall resistance. The analogy that I think works well there is a metal chain running in a loop through your circuit, and resistors are like people's hands grabbing onto it and providing friction. And in parallel, adding a new resistor actually decreases the resistance, and that shows up mathematically because the resistances are all in the denominator here. And the analogy that I like there is the grocery store checkout analogy. So we're at a point now where we can solve some more interesting, more complicated circuit puzzles. Now that we know how to interpret a circuit diagram, and from looking at a diagram, we can get a qualitative sense of how the circuit and the current and voltage are going to behave. We also have some mathematical know-how. We know how to use Ohm's law to calculate specific values at specific points in the circuit. And now we also have these new rules, which are called Kirchhoff's laws, that let us get precise mathematical answers for voltage, current, and resistance in series and in parallel. We can do some more complex things. So let's look at a couple of examples. And for these examples, especially when you're just getting started out, I kind of recommend you follow these 4 steps here. Once you get better at these and you have some practice with these, you don't have to follow these steps. You can kind of decide what you want to do next, and you can find some shortcuts in a lot of problems. But for now, when you're starting out, I think using these 4 steps is a good way to go. And I'll refer back to the 4 steps as we use them. So let's look at these examples. In this first example, we have a circuit. We've got a power supply, and then we've got 3 resistors, and note that these are all in parallel. The resistors are in parallel, and they're in parallel with the power supply. We've got 1 ammeter here, giving us a reading, and we're being asked to find the value of R2, basically meaning we want to know what this resistance is right there. So, to start solving this, I'm going to look at these steps. First step says write V, I, and R at every device or resistor, and write V and I at the power source. So let's go ahead and do that. I've already got R at this first resistor, so I can write V and I there as well. And then R, V, I at the second resistor, and R, V, I at the third resistor. So I've got V, I, R at every resistor, and V and I at the power source. Okay, so that was sort of my first step. Not really doing any math or anything with numbers, just kind of setting things up. Then the next step I recommend is fill in everything you can. So of those values we kind of wrote, put in numbers for as many of them as I can, and use Ohm's law to help you if necessary. Remember, Ohm's law was this fancy, helpful formula. V equals I R. But before we get to that, let's just see if there are any values we can just fill in off the bat. So let's look at voltages first. I do have one voltage that I know, and that's this voltage here of the power supply. So does that help me fill in any other voltages? Well, since all of these guys are in parallel with the power supply, and we know that in parallel, voltages have to be the same, right? Over here, in parallel, voltages are all equal to each other. That means, down here, all of those voltages are going to be the same. So if the first one's 24 volts at this power supply, then that means I'm going to have, 24 volts at the first resistor, 24 at the second, and 24 at the third. Thinking of the skiing analogy here, if you go up a chairlift and it raises you a height of 24 volts or 24 meters, and then you come along, you're skiing along the cat track, and you've got 3 choices of runs to go down. I can either do this first run, or this second run, or this third run, and all of them bring me back to the same spot, then that means they all have to bring me down the same amount. And since they all bring me back to the bottom of the chairlift, they all have to bring me down exactly the height the chairlift brought me up, which was 24 volts. So if the chairlift brings me up 24 volts, then each of those resistors has to bring me down 24 volts. Okay, so those were some voltages I was able to fill in. Let's now see if we can fill in maybe some currents. I do know this current up here through the ammeter. That's measuring a current for me. And so what do I know about currents? Well, currents in series are all the same. So do I have anything in series with that ammeter? Turns out, yes, I do. Although the resistors are all in parallel, the power source and the ammeter are in series. So if there's 1.8 amps through that ammeter, there's going to be 1.8 amps through the power source. With the skiing analogy, that basically means, remember, current is like counting skiers. So if 1.8 skiers go through here, or rather, if 1.8 skiers come through the ammeter, that means 1.8 skiers must have gone up the chairlift because there's nowhere else for them to go in between. I need the same number of skiers to go through both spots. Unfortunately, those 1.8 skiers are going to have to split up when they get to those resistors. Some going this way, some going this way, some going this way. So I have no idea what these currents are all going to be. Although I do know they're going to have to add up to 1.8. I can't figure out what numbers they are right now. Okay, so that's sort of filling in everything I could about the voltages and the current using Kirchhoff's laws. Now let's see if I can use Ohm's law to help. Well, Ohm's law relates V, I, and R. So it means if I know 2 of those things, I can find the third. So here's a situation, here's a place where I know 2 of the things. I should be able to find the third. And here's another situation where I know 2 of the things. I should be able to find the third. So let's go do that math now really quickly. I is going to be V divided by R. So 24 divided by 40, which gives me 0.6 amps. And over here, I is going to be, again, V divided by R. So 24 divided by 60, which gives me 0.4 amps. So now that I've used Ohm's law, I can go back and use Kirchhoff's laws again. Since I know the total current coming into these parallel resistors was 1.8, and I know that had to be split between the three resistors. In other words, the current in the three resistors had to add to that 1.8. If this is 0.6 and this is 0.4, I know this third one has to add with 0.6 and 0.4 to give me 1.8. In other words, the middle resistance is going to be 1.8 minus 0.6 minus 0.4, or 0.8 amps. And now again, I'm in a scenario where I know the current and I know the voltage at this middle resistor. So because I know two of these three things, Ohm's law can be used to find the third thing, which is what I'm looking for in this problem. So I can say R2 is going to be V divided by I, or 24 divided by 0.8, or 30 ohms. So there you have it. That first problem was a good example of these first two steps. Writing VIR at every resistor, VI at the power source, and then filling in everything you can using Kirchhoff's laws for voltage and current, and then using Ohm's law to help you whenever you know two out of those three things. And we basically just went back and forth between Ohm's law, Kirchhoff's laws, Ohm's law, Kirchhoff's laws, until we had what we needed. Now let's do a problem where we're going to get stuck, where we're going to have to go to step 3 and create what's called an equivalent circuit. Example number 2 here works for that. So same initial setup. We're going to write VIR at every resistor. And V and I at the power supply. We're going to fill in what we can, just using Kirchhoff's laws. So let's look at for some voltages or currents that we might know. I don't see any currents that we know, but I do see a voltage that we know up here. So do I have any voltages that'll be the same as that? Well, voltages would be the same in parallel. Everything in this circuit is in series, so I don't think I know any voltages that will be the same as that one. So this problem becomes a little tricky. We really don't know hardly anything as far as voltages or currents. All we know are a bunch of resistances. So pretty quickly, we're at a point where, okay, we set it up, we wrote all these things down. We've tried to fill in any voltages or currents we can using Kirchhoff's laws. And if we got to a point where we knew 2 out of 3 things at any one resistor, we could use Ohm's law, but we weren't even able to get to that point. So we are stuck. And if you get stuck, you're going to create an equivalent circuit by combining resistances. I'll show you what that looks like. So these resistances that I have here, 1, 2, 3, they are all in series, and I'm going to combine them and replace them with a single resistor that has the same effect. And then I'll redraw the circuit. So redrawing the circuit over here, replacing all 3 of those resistors with one looks like this. Now, what would the value of this resistor be? What one resistor would have the same effect as those 3 all combined together? Well, because these resistors are in series, what do I do with resistors in series? In series, resistances, they all add together. So the total resistance here is going to be 3 plus 4 plus 2. Which is 9 ohms. And so now we've created this sort of equivalent circuit. Instead of those 3 resistors, I have just one, but it should have the same effect as them. I've still got a 12-volt power supply here. I just copied that over from my original circuit. It'll have a current, and also this resistor is going to have a voltage and a current. So let's try and solve this circuit instead of the original one. Now, because I've just got one resistor, I can see that it's also going to have 12 volts. If the chairlift brings me up 12, and I've only got one run before I get to the bottom of the chairlift, that one run is going to have to bring me down 12. So those voltages will match. And now, because I know 2 out of 3 things at this resistor, I can use Ohm's law to find I. So I is going to be V divided by R, or 12 divided by 9, or 1.3 repeating amps. And because there's only one path for current to take, if I've got 1.3 amps down there, I'm going to have 1.3 repeating amps up here at the power supply. And this is where these equivalent circuits become really useful. None of this information here that I found at my resistor really directly translates onto my original circuit, because that resistor is not in my original circuit. This 9 ohm resistor was something we made up. It doesn't occur over here. But it causes that equivalent circuit to behave the same as the second one. So the behavior I see at other points in the circuit should be the same. So this 1.3 amps I have up here should be the same as over here. So I can copy that over. And now we can go back to this original circuit, look at what we were being asked to find. We were being asked to find I1, I2, and I3, the currents being read by these 3 ammeters. And because everything here is in series, the current has nowhere else to go. All those currents should be the same. So I1 is going to have to be 1.3 repeating amps. And I2 is going to have to be 1.3 repeating amps. And I3 is going to have to be 1.3 amps. All right, so there's an example that kind of used all of our steps. We set the problem up with V, I's, and R's in all the right places. We tried to find what we could using Kirchhoff's laws, and we would have used Ohm's law if we could get to it, but we got stuck. So we had to make an equivalent circuit by combining resistances. We combined these three resistances, in this case in series, to get this total resistance, and we used that in our new circuit. And then we found once we had V and I at the power supply, things did get a lot easier. Once we had these two things, we were basically done the problem. Okay, so we've got one last example, and the nice thing about this example, it's the first example where we have to combine resistances in parallel, which can be mathematically a bit tricky. So let's dive in here. Same steps as always. We've got V, I, R at every resistor. And at the power supply, we've got V and I. Let's look at the currents and voltages we know and see if we can copy them out anywhere. Well, I don't see any voltages. I do see a current. This ammeter is reading 2.0 amps. So anything that's in series with that should have the same current. So that means my power supply is going to have 2 amps. Then we come around the circuit. We've got these two resistors in parallel. The 2 amps will split, so I don't know how many goes to each. But then it recombines, and I'll need to have 2 amps over here at that first resistor. So we've used Kirchhoff's laws for voltage and current as much as we can. Now, I think we have an opportunity to use Ohm's law over here on the left with R1. Voltage is going to be I times R, so 2 times 8, which gives me 16. Now that I have a voltage, maybe I can use Kirchhoff's laws to find some other voltages. Do I see any voltages that are in parallel with that 16? I don't, so I do think I am still stuck again. So, because we're stuck, we're going to have to make an equivalent circuit. And I'm not too concerned about R1. I've got R1 figured out. The stuff in this circuit that's tricky are these two resistors here in parallel. So in my equivalent circuit, I'm going to combine those two together into a single resistor. So let's draw that out. Okay, here's my original resistor with 8 ohms, 16 volts, and 2 amps. Here's my power supply. Don't know what the voltage is, but the current is 2 amps. And then here is my new equivalent resistor. So again, this power supply and this resistor, they existed in the original circuit. I've just copied them from the original circuit. This new resistor is an equivalent resistor. It doesn't exist in the real circuit, but it will have a resistance that causes the new circuit to behave exactly the same as the old circuit. So what is that resistance going to be? Well, to find the total resistance of those two parallel resistances added together, I'm going to use my formula for finding the total resistance when you combine resistances in parallel. So that is this formula with all the fractions in it. And let's start by copying it out down here where we're going to need it. So 1 over R total equals 1 over R1 plus 1 over R2. And then we would continue for R3 and R4 if we had them, but we've only got 2 resistors that we're combining here. So R1 is 12 ohms. R2 is 24, and that gives 3 out of 24 if you're working with, if you like working with fractions, or 0.125 if you like working with decimals. And if you like working with decimals and fractions, 0.125 can be written as 0.125 over 1. And so a reminder though, that is not our total. 3 over 24 or 0.125 are not equal to our total. They're equal to 1 over our total. So to find our total, I'm going to have to flip those numbers. So if we write this again, say taking the 0.125, I've got 1 over our total equals 0.125 over 1. If I flip both sides of that formula to get our total all by itself, I'll get our total over 1, which is just the same as our total, equals 1 over 0.125, which is equal to 8 ohms. So all that work was just to show that when I combine these two resistors together, they have a total combined resistance of 8 ohms. So my equivalent resistor over here should have a resistance of 8 ohms. So what else might I know about that resistor? Well, it's also going to have a current and a voltage. And since everything in my new equivalent circuit is in series, that means the currents should all be the same. This is 2 amps and this is 2 amps, then this guy should be 2 amps as well. And now, because I know 2 of the 3 things, I can use Ohm's law to find the third. Voltage is going to be current times resistance. So 2 times 8 gives me 16 volts. And now I can go back and use Kirchhoff's law, one of Kirchhoff's laws. Everything's in series, so voltages kind of add together. So if I go down this run and I lose 16 volts, and then I go down this run and I lose 8 volts, that means I have lost a total of 32 volts while skiing. So when I get to my chairlift, how much is it going to have to lift me up to get me to the top of that first run? 32 volts. And that is my final answer. The question was asking me for the potential difference at the power source. Remember, potential difference is the definition of voltage. Voltage is the difference in potential. And that's exactly what we found at the power source. So hopefully those examples give you sort of sufficient initial guidance on how to use these 4 steps up here to start to solve some circuit puzzles using Kirchhoff's laws, Ohm's law, and creating equivalent circuits when necessary.